Have you ever found yourself reaching for a snack even when your stomach isn't quite, growling? Or maybe you've felt completely full, but the aroma from that dessert menu still somehow called your name? It's a common thing, right? And it hints at something really profound. Your appetite isn't just some simple on-off switch. Not at all. Instead, you should imagine this complex neuroendocrine orchestra inside you. It's constantly playing a symphony of signals, controlling when, what, and how much you eat. Welcome to the deep dive. Today we're going on a really fascinating journey, peeling back the layers on this intricate world of appetite control. And for you, as future medical professionals, getting a handle on this system isn't just, well, interesting, it's absolutely crucial. Crucial for understanding metabolic health, for tackling conditions like obesity, which, let's face it, you'll see a lot in clinical practice. So our mission today is pretty clear. We're going to try and demystify the brain's command center for appetite. We'll decode that symphony of peripheral hormones involved, and really importantly, differentiate between eating out of genuine biological need versus, your pleasure.
That need versus want distinction is key.
Exactly. And we'll also touch upon how this incredibly complex system can sometimes go awry and explore some of the exciting new therapeutic frontiers that are emerging. Okay, to really anchor our understanding, let's start with a little thought experiment. Imagine your body has a central fuel gauge and a sophisticated control panel. As we start our journey into the brain, where exactly is this primary control panel located, and what are its two main switches that dictate if you feel hungry or full?
Yeah.
Keep that in mind. Okay, I'll circle back to it later.
That's a great way to frame it, because before we dive deep into the brain itself, it's really vital to grasp the foundation: energy balance. This is basically the equilibrium, right? Between energy intake, the carbs, lipids, proteins you eat, and your energy expenditure. It covers your basal metabolic rate, physical activity, even the energy used just digesting food, which we call diet-induced thermogenesis.
It's exactly like managing a bank account, isn't it? If your income, your energy intake consistently matches your expenses, your expenditure, well, your body weight stays stable. More income than expenses, you start accumulating savings, often as fat. More expenses than income, you start dipping into those savings. And as clinicians, we know an imbalance here. Well, it can lead to pathological weight gain or loss. Both carry significant health risks. It's all about finding that balance.
And at the very heart of maintaining this delicate balance, as you mentioned, is the hypothalamus. This tiny but incredibly powerful part of your brain isn't just a master thermostat for temperature. It's a central regulator for so many essential homeostatic processes, energy balance included.
And within that master thermostat, we find the real central switchboard for appetite, the arcuate nucleus, the ARC. It's nestled deep within the hypothalamus. But what makes the ARC particularly fascinating, just vital for understanding how our body talks to our brain about food, is its unique accessibility.
Yeah, that's the intriguing part. The ARC isn't fully sealed off by the blood-brain barrier. Think of it like a central dispatch office that has this crucial open door. It can receive urgent messages directly from the bloodstream, telling it about your body's energy status, circulating glucose, fatty acids, hormones. This direct access lets it constantly collect info about energy stores. And then it modulates both energy intake and expenditure. It's a really sophisticated monitoring system.
So the ARC is getting all this intel about our fuel levels. How does it then process this information and decide, okay, time to signal hunger, or nope, we're full, it must have its own internal team, right?
It absolutely does. The arcuate nucleus houses two main types of neurons, each playing a distinct role. First, you've got the primary neurons. Think of them as the sensing specialists. They're directly wired to detect those metabolites in the blood and respond to the hormones circulating through the body.
Okay.
Then you have the secondary neurons. These act more like action coordinators. They get input from the primary sensors and then orchestrate a response, often sending signals out via the vagus nerve or to other key hypothalamic areas.
Okay, let's really unpack those primary neurons, because this seems to be where we find our two main internal switches for hunger and fullness. We're talking about the orexigenic neuron and the anorexigenic neurons, correct?
Precisely. The orexigenic neurons are your hunger-promoting signals. They release neuropeptide Y, that's NPY, and agouti-related peptide, or AGRP. When these neurons fire up, they're basically shouting, "Eat no W, fuel is low."
Right.
We can definitely think of them as the go-go gang, pushing us towards food.
And on the flip side, we have the anorexigenic neurons, our stop-stop squad. They're all about promoting satiety, that feeling of fullness. These neurons release pro-opiomelanocortin, POMC, and cocaine and amphetamine-related transcript, which is CART.
Mm.
And it's really important for you as medical students to remember that POMC gets cleaved into alpha melanocyte stimulating hormone, MSH, and that is a powerful promoter of satiety.
Absolutely key.
So when these stop squad neurons are active, they send out those calming messages. You're good, hold off, fuel levels are fine.
And it's that constant interplay, that delicate balance between the go-go gang and the stop squad within the ARC that's so fundamental. They're constantly talking to each other and to other brain areas, ultimately shaping our eating behavior from moment to moment.
It's really incredible, this tiny part of our brain acting as such a central hub. But how does this conductor know what's happening out in the rest of the body? That's where I guess our peripheral symphony of signals really comes in. So here's our next question for you to think about. We know the brain's internal switchboard now, but what about those external signals? If your stomach is completely empty, really demanding fuel, there's one specific hormone that just screams, "Feed me." Which peripheral hormone is that? And how does it specifically activate those go-go neurons in the ARC to make you feel hungry? Let's dive into that.
Yeah, exactly. The ARC doesn't work in isolation. It's in constant communication with the rest of the body. Through this sophisticated gut-brain network, mediated by hormones in the blood and key neural pathways like the vagus nerve. And this is where those powerful peripheral signals really make their entrance.
And when it comes to that undeniable feed me signal, the absolute star of the show is ghrelin, Ghrelin. It's our main hunger hormone, the one causing that rumbling, growling signal you feel.
That's the one.
It's released from your stomach, specifically when it's empty, and it acts as the only major appetite-stimulating hormone we're focusing on today.
And its action is remarkably direct, actually. Ghrelin specifically targets and stimulates those orexigenic NPY-AGRP neurons in the arcuate nucleus. It gives a direct push to that go-go message.
Right, to the source.
Exactly. And what's also important clinically is that stomach distension, just the physical filling of the stomach,
Right.
effectively inhibits ghrelin release. So the act of eating itself starts to put a natural brake on that specific hunger signal.
Okay, so ghrelin gets the hunger going. Now let's talk about the counter signals, the satiety signals. This is like a whole choir of hormones telling us, okay, stop eating now. First up, the big player for long-term regulation, leptin. I like to call it the fatometer hormone.
That's actually a perfect analogy because leptin is a polypeptide hormone and it's released directly from adipocytes, our white fat cells. The levels of leptin circulating in your blood are directly proportional to your total fat mass. So it gives the brain this continuous long-term readout of your body's overall energy stores.
And its action is absolutely crucial for long-term appetite suppression, isn't it?
Yes, leptin actively inhibits those orexigenic hunger-promoting neurons. And at the same time, it stimulates the anorexigenic satiety-promoting neurons in the ARC.
Double whammy.
Pretty much.
Yeah.
And it even has another neat trick. It induces uncoupling proteins, UCPs, in mitochondria, which basically leads to energy dissipation as heat. So it's not just saying stop eating, it's also subtly boosting energy expenditure.
Which is vital from a clinical standpoint. I know leptin treatment works dramatically for the very few people who genetically lack it.
That's true. Those rare cases really highlight its importance.
But for most people with obesity, the problem isn't a lack of leptin, it's leptin resistance, right?
Exactly. That's the major clinical challenge. The body's often producing plenty of leptin, sometimes very high levels. But the brain isn't getting or properly responding to the "I'm full" or "we have enough reserve" signal. This resistance means that simply giving more leptin often doesn't work for the majority of obese patients, forcing us to look at other therapeutic strategies.
Okay, then we have insulin, our body's sugar cop hormone, released from the beta cells of the pancreas, mainly when blood glucose rises after a meal.
Insulin also contributes to suppressing appetite. It acts as an anorexigenic signal. Though its role here is generally considered less powerful, maybe less direct, than leptin's long-term signal. Clinically, of course, we know insulin resistance is tightly linked to both obesity and type 2 diabetes. So understanding its contribution to satiety is another piece of that complex metabolic puzzle we need to consider.
And co-secreted right alongside insulin from those pancreatic beta cells, we find amylin, another polypeptide hormone.
Right, amylin adds another layer. It further suppresses appetite. It decreases glucagon secretion, which helps keep blood sugar in check, and it slows down gastric emptying, all of which helps you feel fuller for longer after eating.
So it works on multiple fronts.
It does. And it's effective enough that an amylin analog, a drug called pramlintide, is already approved and used clinically for type 2 diabetes. It's a great example of harnessing these natural satiety mechanisms therapeutically.
Beyond the pancreas and our fat cells, the gut itself is just buzzing with hormonal activity, sending these crucial messages up to the brain. What are some of those key players coming from the digestive system that add to this feeling of fullness after we eat?
Oh, that's an excellent point. The gut really does contribute a whole chorus of satiety signals.
Hmm.
It's not just one or two. We have hormones like peptide tyrosine, or PYY. There's glucagon like peptide 1, GLP-1, called spistokinin, CCK, and oxyntomodulin. These are mostly released from different parts of the small and large intestines, generally in response to food actually passing through.
So after we eat, these gut hormones just spring into action. How do they kind of work together to tell the brain, okay, we're satisfied?
Well, they collectively act to inhibit those stimulatory or exogenic neurons and stimulate the inhibitory anorexigenic neurons back in the ARC,
Mm-hmm.
essentially putting the brakes on wanting to eat more.
Okay.
They also slow down how quickly the stomach empties, which definitely contributes to feeling full. And they can reduce gastric acid secretion too. Among this group, GLP-1 has really emerged as a major player because of its powerful anorexigenic effects.
Yeah, GLP-1 seems to be a real superstar in this whole conversation, but I seem to remember hearing it has a kind of practical challenge, especially for making drugs out of it.
You're absolutely right. What's fascinating and was a big hurdle for drug development initially is that natural GLP-1 has an incredibly short half-life. We're talking like 5 minutes.
Wow, that's fast.
It is. It gets rapidly broken down by an enzyme called DPPIV. But despite that, scientists figured out how to make longer-lasting versions, the GLP-1 receptor agonists. And these have become incredibly important treatments, which we'll discuss more, because their ability to regulate appetite and blood sugar is just so profound.
Right.
CCK, another one, is mainly released from the upper part of the small intestine, the duodenum and jejunum. Levels rise pretty quickly after a meal, and it dose-dependently cuts down food intake, plus it stimulates the gallbladder. And oxyntomodulin, often released alongside GLP-1, also ships in to increase satiation and reduce food intake. It really is a team effort from the gut.
Okay, so we've really mapped out the body's biological fuel gauge here. And the hormones signaling true hunger or fullness, that's the homeostatic system, guiding our need to eat. But let's be real, sometimes we eat for reasons completely separate from biological necessity. We've all been there, right? Finishing a perfectly good meal, feeling satisfied, but then suddenly craving that rich chocolate cake, even though your stomach is saying, nope, no room.
The cake phenomenon.
Exactly. So that brings us to our next key question for you. What is the distinct regulatory system that drives our wanting to eat? The pleasure, the taste, the reward, even when we're not technically hungry. This is a huge piece of understanding modern eating patterns.
That's a critical distinction,
Yep.
absolutely. And it leads us straight into understanding the two fundamental paths controlling appetite: the need versus the want.
Okay, so the first path, which we've mostly covered, is the episodic homeostatic regulatory system. This is our basic need to eat system. Its whole focus is responding to that fundamental biological requirement for food because our body genuinely needs fuel.
Precisely. This system involves constantly sensing fuel availability in the blood glucose fatty acids and reacting to all those central and peripheral signals we've detailed. The ARC neurons, ghrelin, leptin, insulin, all those gut hormones like GLP-1 and PYY. It's essentially your body's autopilot for survival, just tirelessly making sure you get the essential nutrients to keep everything running.
But then there's this completely different beast. The hedonic regulatory system, our wanna-eat system. This one is all about eating because we feel like it. It's driven purely by pleasure, by reward, by sensory experiences. It's what makes that cake irresistible, even if your biological fuel tank is completely full.
Exactly right. This system responds to powerful reward signals, things like endorphins. And crucially, it involves higher brain areas beyond just the hypothalamus. We're talking about regions heavily involved in reward circuitry, like the hippocampus, the nucleus accumbens, the amygdala.
Ah, the reward centers.
Precisely. And different neurotransmitters are involved here too. Opioids, GABA, glutamate, cannabinoids all play roles. You could think of this system as your brain's gourmet chef, always searching for the next delicious, rewarding experience, pretty much regardless of the actual fuel tank level.
Okay, so let's be crystal clear here, especially for our future clinicians listening. When we asked about the system driving the wanting to eat, the hedonic regulatory system does not primarily respond to biological need. Its main driver is reward and pleasure.
Correct. That distinction is absolutely fundamental for understanding eating behaviors, especially in our modern food environment.
Okay, Given all this incredible complexity we've just outlined, the ARC, the hormones, these two distinct systems, it's maybe not that surprising that this finely tuned orchestra of appetite control can sometimes, well, break down. It seems incredibly vulnerable to disruption from all sorts of factors, internal and external.
Absolutely. Beyond just internal biology, external factors definitely play a significant role. For instance, exposure to certain chemicals, particularly endocrine disruptors, compounds found in some plastics or pesticides that can interfere with our natural hormone systems. These can potentially throw this delicate balance off kilter. And what's more, highly and ultra-processed foods, often categorized using the Novier system.
Right, that system classifies food by processing level.
Yes. And those foods have been strongly implicated in a range of metabolic and behavioral changes. Often it's thought by sort of hijacking that hedonic, reward-driven system.
It's like you said, an orchestra. And suddenly some instruments are wildly out of tune or playing the wrong notes entirely. It leads to discord, to chaos.
Good analogy.
That's essentially what happens when appetite control gets disrupted. So what are we doing about it? Let's talk strategies for body weight reduction, moving from those foundational lifestyle changes to the really cutting-edge pharmacotherapy we're seeing now.
Well, we always start with the foundations. Lifestyle interventions. That means dietary changes, maybe calorie restriction, maybe specific approaches like low-fat diets, but consistently combined with increased physical activity. And importantly, psychological therapies like cognitive behavioral therapy, CBT, are often vital as an adjunct. They help patients navigate the behavioral and emotional aspects of eating and weight management.
But when lifestyle changes alone aren't achieving the necessary goals, pharmacotherapy often enters the picture. We have established drugs like the GLP-1 receptor agonists, which have truly revolutionized the field. Names you'll definitely hear are semaglutide and liraglutide.
Oh, absolutely. These drugs have really widespread beneficial effects. They enhance satiety, making people feel fuller. They significantly reduce overall food intake and appetite. They slow gastric emptying. They even suppress gastric acid, enhance insulin secretion, and inhibit glucagon secretion.
Wow, quite a list.
It is. And all of this together leads to much improved glycemic control and, crucially, substantial weight loss. They're incredibly powerful tools for metabolic health.
And then there's orlistat, which works quite differently by inhibiting fat absorption in the gut.
Correct. It blocks gastric and pancreatic lipolysis.
But what's truly exciting now, I think, are these incredible new developments in drug discovery, particularly the dual and even triple co-agonists that are just pushing the boundaries of what we thought was possible.
This is really where things get cutting edge, and it's vital for you as future clinicians to be aware of this evolving landscape. Tirzepatide, for example. It's the first approved dual coagonist, uniquely targeting both the GLP-1 receptor and the GIP receptor. GIP is glucose-dependent insulinotropic polypeptide.
Okay, two targets at once.
Exactly. It's already approved for type 2 diabetes based on the results from the SURPASS clinical trial program. And it's currently undergoing extensive phase 3 trials specifically for obesity in the SURMOUNT program.
And the results coming out of those SURMOUNT trials have been pretty stunning, haven't they?
Truly remarkable. The SURMOUNT-1 trial, which looked at non-diabetic individuals with obesity over 72 weeks, it showed that tirzepatide, when combined with lifestyle intervention, led to an average weight loss of between 15% and nearly 21%.
That's huge for a medication.
It really is. Compare that to just about 3% weight loss with placebo plus lifestyle. These are unprecedented figures for pharmacotherapy, and we're also seeing the development of other coagonists like GLP-1 combined with amylin or GLP-1 combined with glucagon. And it's worth remembering that glucagon, while known for raising blood glucose, also has this interesting dual role where it seems to reduce food intake, increase satiety, and maybe even boost energy expenditure.
And pushing things even further, I understand there are even triple coagonists in development, targeting GLP-1, GIP, and glucagon all at once.
That's right. It really showcases this multi-target approach scientists are taking to tackle obesity's complexity.
Beyond these incretin-based therapies, what other novel targets are on the horizon?
Well, other exciting areas include agonists for the melanocortin-4 receptor, the MC4R. A drug called setmelanotide targets this. Now, setmelanotide is particularly important because it's approved for treating ultra-rare genetic disorders that cause severe obesity, specifically conditions caused by mutations in the leptin receptor gene, or the POMC gene itself.
Ah, connecting back to those pathways we discussed.
Exactly. Individuals with these conditions often suffer from profound, unrelenting hunger, what we call hyperphagia, and develop severe obesity very early in life. Studying setmelanotide helps us understand the fundamental genetic underpinnings of appetite control and see what happens when a key signaling pathway is broken.
Fascinating.
We're also seeing other approaches like amylin analogs, such as cagrilintide, and activin type 2 receptor agonists, like bimagrumab, moving through clinical trials, all trying to restore balance to this incredibly complex system.
And of course, we should mention that for individuals needing significant and sustainable weight reduction, bariatric surgery remains a very powerful and effective option.
Wow. So we've really covered a lot of ground today, a truly intricate landscape. We started right in the brain's central command center, didn't we? The arcuate nucleus, with its go-go and stop neurons orchestrating basic hunger and satiety.
The hypothalamic hub.
Then we explored that rich symphony of peripheral hormones, ghrelin yelling feed me, leptin reporting on fat stores, GLP-1 and others signaling from the gut. And we saw how these signals contribute not just to our biological need for food, but also to that powerful desire for rewards, the hedonic drive.
It really is an incredibly complex and beautifully integrated system, dictating one of our most fundamental physiological drives, eating. Understanding all these components and how they interact is truly foundational knowledge. And just to circle back and make sure we nailed our initial questions, your body's primary appetite control panel is indeed the arcuate nucleus within the hypothalamus. And its main switches are those orexigenic, hunger-promoting, and anorexigenic, satiety-promoting groups of neurons.
And for that second question, the hormone screaming feed me from an empty stomach is ghrelin. It directly stimulates those hunger-promoting neurons, sending that unmistakable signal to find food.
And finally, that system driving the wanting for the extra dessert, the one operating beyond just biological need, that's the hedonic regulatory system, focused entirely on reward and pleasure, involving those higher brain areas like the hippocampus and nucleus accumbens.
And what's becoming increasingly clear is how these two systems, the homeostatic and the hedonic, once merely thought of as quite separate, actually interact and influence each other constantly, really shaping our eating behaviors in profound ways, especially in today's world, with readily available, highly palatable foods.
So, as future medical professionals, getting a solid grasp on this intricate orchestra of hormones and brain signals is going to be absolutely vital for you. How might this detailed knowledge, knowing about both the homeostatic and the hedonic drivers, empower you? How might it help you approach patient care in obesity and metabolic disorders more holistically? Maybe, just maybe, by helping you recognize that telling someone to just have more willpower barely scratches the surface of this incredibly complex biological story.
That's a crucial point.
Keep exploring, keep questioning, keep learning, because this dynamic field is constantly evolving and only just beginning to reveal its full potential for improving health.